Let's go over the components of a microcontroller. This is the outline for this video, and we're going to start with some examples. This is a Samsung Gear Fit fitness tracker. If we reverse engineer the system, we can see it's using an STM32F4, similar board to the one that you're using for this class. The next one is an iPhone 4. It uses an ARM 7. Here you have the PIC 16F877, and these are examples of architectures, and I want you to pay attention on type of logic components that you can recognize on these schematics. This is the PIC. You can pause the video so you can take your time. This is an AVR. This is a smart card, like similar to the ones that you use to pay your bills. An ARM core data flow model. And the question that I ask is, what do they have in common? And if you pay attention, all of them have an arithmetic logic unit to perform additions and subtractions, some sort of memory elements, flip-flops, memory, registers, multiplexers, and generic purpose input and output signals. Let's go over a simple CPU, and let's go over assembly instructions and examples. So we saw that all those architectures, all those microprocessors, they have an arithmetic logic unit and a bunch of registers around, and a control unit that is going to control on how these registers and all additions and subtractions are going to be performed. If you are a CPU student, you took advanced digital design, this should be familiar with you. But if you are an electrical student, you probably never saw this, so take your time to understand these concepts. And we're going to combine assembly instructions with this hardware logic. And let's say that I want to perform this specific assembly instruction, load whatever is present on the data inside of this register Rx. So data is information that is coming from the outside, and I want to load it, let's say, on register R0. Notice that I have a bus, which is a common wires that are being shared by these registers. This module over here that you see in front of all registers is called a tri-state. Is going to allow you to select if you want data coming from the register on the bus or not. So do you want data available here or not? So this is how you use the tri-state component here to control that. So I want to load the data into the Rx. If nothing is going on, pretty much what is happening is this data is going to enter the bus until it goes inside of my register 0. So notice that I don't need more than just one clock in order to perform this assembly instruction. Let's go over another example. Let's say now that I want to move the contents from one register to the other register. So let's say that I have information on this register R3, and I want to put that information, comes out and goes inside of that register over there, R0. So same thing applies here, not that complex, probably one single clock is more than enough in order to execute that operation, also a simple instruction. Let's look at a more complex instruction. Now I'm adding. So let's say that I'm saving a value 3 on register 4 and a value 4 on register 3, and I want to add those two values. In that case, now it's a little bit more complex because I cannot have both registers putting this information on the bus. The bus is shared by these two components. I can only have one of those numbers at a time on that bus. So how do I solve this? I need a little bit more clock cycles in order for this to happen. I might, for example, load on the first clock cycle this number 3 inside of your accumulator. And then once that is done, I then can load what is inside of my register number 4 on the other side of my arithmetic logic unit. So now I have the 4 over here, and I have the 3 over here, and now I can execute the operation and get an answer that is going to be loaded, let's say, on register number 3. So notice here that the colors that I'm using can represent the amount of clocks that you need in order to perform this assembly instruction. So one way of visualizing this is actually putting a table, and notice that my load and move, they just need one clock cycle. This is what you have here, T1, T2, and T3, how many clock cycles you need. And your addition, as we saw, we had 3 colors, they need 3 clock cycles. All these just to explain the famous how many cycles per instruction do you have, which is important when you're programming microprocessors. This is where it's coming from. I just need, let's say, 1 cycle for the load and move, and for the add I need a little bit more cycles. So this is going to slow down a little bit your code. So let's go over another concept of execution flow, which is pipeline. And pipeline is 3 stages. We have fetch, which you load an instruction from memory. That means that I will have a memory, external memory over here. This is my memory, and somehow I need to get information from that memory, that instruction, into my CPU. Then you have the decode part, so I need to decode if it's a load or an add, and then at last the execution part. We just saw how to execute those assembly instructions. The fetch and decode, it's part of another topic. But all these just to talk about an important concept, which is pipeline. I can actually accelerate the way that I execute those assembly instructions. So notice here that the fetch, the hardware to do the fetch is done here. Then you have the hardware to decode the fetch, and then you have the hardware to execute those assembly instructions. We just went over this part over here. We didn't cover the other hardware, but I can abstract a little bit more, and what I have is the fetch, instruction fetch, then the decode, and then the execution of this. Alright, just have in mind this. We'll get back to this block diagram or this hardware, and let's just go over an abstraction of pipelining. Let's say that I want to wash, dry, and then fold a set of dirty laundry, and I have 4 loads of that. So one way of doing that is I start by washing the clothes, then I dry them, and then I fold, and then I wash the other load, dry, fold, and so forth and so on. And you'll probably know that this is probably not very efficient. And the question is, can I run these tasks at the same time? Well, as long as they are independent from each other, there is no problem doing that. So if I actually go here, and when I'm drying the first load, if I can wash the second load, I'm executing these 2 actions at the same time. And the same repeats for the next loads, the following loads. Same thing applies for this pipeline concept to run assembly instructions. If each part of these is independent hardware, can I run more than one assembly instruction at the same time? And the answer is yes. That's what pipelining is doing. If I'm able to fetch while I'm decoding another one and executing another instruction, that's totally fine. And that's what it's called pipelining. And I can accelerate the process. Instead of taking 3 clock cycles to run, or let's say 4 clock cycles to run 2 instructions, I can actually run 2 instructions in the time of 1 on those 3 clock cycles.